Welcome back to our Computer Systems unit. In this lesson, we will learn how the computer stores and represents real numbers. As always, we will have learning intentions for the lesson. We'll learn how 8-bit positive and negative real numbers are stored and represented using floating point representation, and we'll learn what the relationship is between the number of bits assigned to the mantissa and the exponent and the range and precision of those floating point numbers. Again, we will have success criteria, which should be used as a tool to measure your progress throughout the lesson. To start with, let's look at some basic number conversions. Say we want to represent the number 15.25. We could say that this can be written as 0.1525 times 100, only written in a different way. We've shifted the decimal point 2 places to the left, hence times the 100. Again, this is the same as 0.1525 times 10 to the 2. 100 is the same as 10 to the power of 2. The same example can also be written as 1111.01 in binary. Moving the decimal point in front of the most significant bit will result in 0.111101 times plus 2 to the power of 4. If the exponent is converted to binary, then we will have 0.111101 times plus 2, 100. We have shifted the decimal point 4 places to the left, giving us an exponent of 4, and we then have converted this exponent to binary. Luckily for us, we don't have to carry this process out every time. Usually at higher level, we are given a binary number to work with. Let's move on and look at some basic rules. As the decimal point is always deemed to be in the same place, which is before the most significant bit of the binary number, then we do not need to store this. Also, as this is a binary number, then we know that the base number is 2. Again, we do not need to store this. All that we need to store is the sign bit, the mantissa, and the exponent. Let's look at our first example. We're going to convert the binary number to floating point representation. We will use a 16-bit mantissa, including the sign bit, and an 8-bit exponent. Our number will be 110.001. The first step will be determining the sign bit. The sign bit will be a 0 for a positive number, or a 1 for a negative number. In this case, our sign bit will be 0 because we know this is a positive number. In the second step, we will shift the decimal point in front of the most significant bit. In this case, we will shift the decimal point 3 places to the left. This gives us an exponent of 3. In step 3, we can now complete and show our 16-bit mantissa. Again, make sure you include your sign bit as one of those 16 bits. Our sign bit will be 0, followed by our number 110001. We will then make up the rest of the mantissa using 9 zeros to make up our 16 bits. Our full mantissa is 01110000000000. In step 4, we will now show our exponent. We will write out our 8-bit exponent by adding the extra bits. Now remember, our exponent was 3. That's because we moved the decimal point 3 places to the left. We found that out in step 2. We can now show our 8-bit exponent. Our fifth and final step will be to show our entire floating point number by placing our mantissa and our exponent next to each other to show the entire 24 bits that we have been asked to represent. 16 bits for our mantissa and 8 bits for our exponent. Now let's look at our second example. We're going to convert the binary number to floating point representation. Again, we will use a 16-bit mantissa, including our sign bit, and an 8-bit exponent. This time the number we will convert will be minus 10111.11, and we'll show this in the next few slides. We will again follow the steps that we showed in the last example. Step 1 will be to determine the sign bit. Again, a 0 for a positive number or a 1 for a negative number. In this case, we clearly see we have a negative number. Therefore, our sign bit will be 1. In step 2, we will shift the decimal point in front of the most significant bit. In this case, 5 places to the left. This gives us an exponent of 5. In step 3, we will show our entire mantissa, writing out all 16 bits. Again, we will do this by including the sign bit and adding extra bits to make up those 16 bits. We have a sign bit of 1, followed by our number 1011111, then made up by adding an extra 8 zeros. This will show our entire 16-bit mantissa. In step 4, we will convert our exponent to binary and show this using 8 bits. Remember, our exponent was 5. We found this out in step 2. We would represent this exponent using 8 bits as follows: 00000101. This would be our 8-bit exponent. Finally, in step 5, we will show our entire 24-bit floating point number. We will do this by placing our 16-bit mantissa, which includes the sign bit, next to our 8-bit exponent. Let's move on to our third example. We're going to convert the binary number again into floating point representation. As we can see, this number is slightly different. We have the number 0.000000011011. Again, we will use a 16-bit mantissa, including our sign bit, and an 8-bit exponent. Again, in step 1, we will determine the sign bit. 0 for a positive number, 1 for a negative number. In this case, we have a sign bit of 0 because we have a positive number. In step 2, we will shift the decimal point in front of the most significant bit. In this case, we will move the decimal point 7 places to the right. Moving the decimal point to the right means that our exponent will be negative. In this case, this gives us an exponent of negative 7. We now have the first part of our mantissa, 11011. In step 3, we will show our entire 16-bit mantissa, including our sign bit. We have a sign bit of 0, then our number 11011, and we will follow this by including an extra 10 bits, all zeros. This will allow us to lay out and show our 16-bit mantissa. In step 4, we will show the exponent. In this case, our exponent was a negative value. Remember, it was negative 7. We found that out in step 2. As this is a negative value, we need to carry out 2's complement. Firstly, we will lay out our 8-bit exponent in positive format. We will then invert this value, which means the zeros will become 1s and the 1s will become zeros. Finally, we will add 1 to this value. We can now show our 8-bit exponent. This is laid out in a negative format. Finally, in step 5, we will lay out and show our entire 24-bit floating point number by again placing our 16-bit mantissa, including the sign bit, next to our 8-bit exponent. We'll now look at our fourth and final example. In the previous 3 examples, we have looked at different combinations of positive and negative mantissa and exponent. In example 1, we looked at an example with a positive mantissa and a positive exponent. In example 2, we looked at an example with a negative mantissa and a positive exponent. In our last example, in example 3, we looked at a positive mantissa with a negative exponent. In our fourth and final example, we will look at a negative mantissa and a negative exponent. Let's move forward with this fourth example. Again, we're going to convert the binary number to floating point representation. We have the negative number negative 0.0000000111. We will represent this using a 16-bit mantissa, including the sign bit, and an 8-bit exponent. Again, in step 1, we will determine the sign bit. 0 for a positive number, 1 for a negative number. In this case, we have a negative number. This means our sign bit will be 1. In step 2, we will shift the decimal point in front of the most significant bit. In this case, we will move the decimal point 6 places to the right. Again, this means that our exponent will be negative. This gives us an exponent of negative 6. We can also identify the first part of our mantissa. 111. We can now show and lay out our 16-bit mantissa. This will include the sign bit, which is 1, our number 111, and by adding an extra 12 bits, all zeros, will give us our 16-bit mantissa. Again, our exponent is a negative value, and as such we need to carry out 2's complement. To do this, we will write out our 8-bit exponent in positive format. Our exponent is negative 6. We'll then invert, which means we will turn our zeros to 1s and our 1s to 0s. We will then add 1. In this case, remember that the first unit place already had a 1. Therefore, this is turned to a 0, and we move up the unit placings to an appropriate place, which is our second under the number 2. We then turn this to a number 1. We can then show and lay out our 8-bit exponent in negative format. 11, 11, 10, 10. This is our exponent. Finally, in step 5, we can show our entire 24-bit floating point number by laying out our 16-bit mantissa, including our sign bit, alongside our 8-bit exponent. Let's now look at the relationship between the number of bits in the mantissa. If we add more bits to our mantissa, this will increase how accurately we can represent our number. This will also decrease the range of numbers that can be represented. On the other hand, if we increase the number of bits to our exponent, this will increase the range of numbers that we can represent, and in turn will decrease the accuracy of the numbers that can be represented. Thanks again for watching. Please subscribe for new content.